Hey everybody, today I'm going to do another math problem, and the math problem that we're doing today actually is an example, okay? It's an example that we're doing on limits, and the study of limits is a very important, especially when we are doing calculus, right? Calculus is all about analyzing problems, right? So limits help us to analyze problems in calculus 1 and up to calculus 2, right? And and of course, we never stop analyzing problems in mathematics. We always have to be analytical when we solve problems in mathematics. Doesn't matter if you take differential equations or you're taking calculus 3. Okay, but or geometry, any math problem is statistics, right? Any problem is a very important to analyze the problems when you're doing the problems. That way the problems make more sense, right? So I'm going to do an example, okay, and then of limits. And the definition of limits is a long definition, but I just wrote two questions right here on this board, right? Because I cannot write the whole definition of limits because it's big. It will cover like 3 different boards of this to write every single thing. But when we solve a problem, we are going to ask the following questions. Okay, one of the question is, as x get closer to a number a, right? To a certain number a, but x cannot equal a, thus the function value of f of x get closer to some real number L, right? Well, remember that A is the domain, okay? So A is the domain of the function, and the real number L is the limit that we're getting when A is when x is approaching A, but not necessarily equal A, right? Now the next question is, can we make a function value f of x as close to L as desired by choosing x by choosing x sufficiently close to A but not equal A? Okay, let's read again the question. Can we make a function value f of x as close to a certain number L, in other words, a certain limit L, as desired by choosing x sufficiently close to A but not equal A? Okay, if we can answer these two questions, yes, then we can use this definition. As f of x approaches L, f of x approaches L as x approaches A. In other words, f of x approaches a certain limit, a certain real number, as x approaches A. Okay? So now this is the example, okay, The example is f of x equal x cubed over 3x minus 6, right? Now, using the definition, okay, remember that x cannot equal a. It can get closer to a, but not equal a. Now, if we look at this function right here, and we want to take the limit, right? Limit as x approaches a, okay? As x approaches some number a, right? So, limit as x approaches some number a. Well, if we want to take the limit of this function, okay, let's say what number it is in the domain of this function. Okay, can any number be in the domain? That's the question that we need to ask. Can any number be in the domain? Well, we need to be careful. Why? Because the denominator cannot equal 0. Okay? In an expression like this, that we have a rational expression, because it's a rational expression, we cannot have a 0 in the denominator. Okay? So what I'm going to do is I want to prove that some number is not in the domain. Okay? So I want to go ahead and see what is the numerator. What make it the denominator equal 0? Okay? So I have a 3x, right? I have a 3x. Okay? Let's say that 3x minus 6 at the bottom, right? So 3x minus 6. Let's say that x equal 2. Okay? When x equal 2, then I have 2 cubed minus 2 times 2 squared over 3 times 2 minus 6, right? Well, 2 cubed is 8 minus 4 squared is, 2 squared is 4 times the negative 2 is negative 8, okay? On the bottom I got 2 times 3 is 6 minus 6, right? I got 8 minus 8 is 0. 6 minus 6 is 0. Okay, look at this. This is undefined. Why? Because you cannot divide by 0. Okay, so if you divide 0 by 0, it's still undefined. You can divide 0 by a number, but you cannot divide 0 by 0, right? Or any number divided by, any function divided by 0 is undefined, okay? So I noticed that a cannot equal 2. So a is not in the domain of this function, right? So if a is not in the domain, what can I do? Okay, to make this number closer and closer to a but not equal a. Well, let's make it a little table. What I did a little table and look for numbers closer and closer to 2 but not equal 2, right? So if you get 1.9, right? 1.9 is going from the smallest to the largest, right? 1.9, the limit of So the function f of x is equal to 1.203333, right? At x equal 1.99, the function f of x is equal to 1.32003333. Okay? At x equal 1.999, I got the function is 1.3320033. Look at these numbers. This number right here, it seems like they are increasing a little bit, slowly increasing. Okay? Look, when I have 4 nines after the decimal point to the right, I get 1.3332000, all right, and so forth and so forth. Notice that this number almost stay constant. At the end, I got 333 after the decimal point. Okay, so I went 1, 2, 3, 4, 5, 6 digits to the right, and I got almost the same number after 1.99. Notice that I got a 3 in this column all the way down. Okay? So that means that I am approaching some certain number. I am approaching, the limit is approaching to some real number. Okay? Now, this is going from left to right. Right? This is going from left to right. Okay? Why? Because I picked 0.9 first and I am increasing closer to 2. Right? Now, what I did, I made another table going from right to left. Okay? Going from right to left. And I pick to the right of the decimal point, I pick, okay, because notice that I went over here, I start at 1.9. I'm going to the right, approaching 2 from left to right. Now I am approaching 2 from right to left. So therefore, I have to start after 2. Okay? After 2. So after 2, what is the first number? It's 2.1, right? 2.01, 2.001, 2.001, 2.0001, and 2.0001. And notice that I am almost getting the same number at the end. Because the number of x was greater, I got a result for f of x is greater. Look at this, 1.47. On the next number, I am getting 1.34. And the next number I'm getting 1.33. And the next one number I'm getting 1.33, 33, and 33, and so forth and so forth. Until I get this number right here is closer to this number. Notice that I am approaching 2 from both sides. I am approaching 2 as x gets closer to 2 from left to right, and also as x is getting closer to 2 from right to left, right? So notice that the limit is almost getting close to certain number. The limit is getting close to a certain number, to equal to a certain number by approaching by getting a equal by letting x equal a, by letting x approaches a from both sides, but not necessarily equal a. So x approaches a, but x does not equal a. Okay, so this is what I'm doing. Okay, so now we know that that definition works for this problem, because I am approaching a certain number. Matter of fact, this number you can leave it as it is. I mean, you can leave that, you can round it off to two decimal places, and you got enough numbers on both sides to make those numbers equal, right? The number L is approaching the same number on both sides. When I let x equal x approaches a on both sides, the number L is almost the same. Okay. Now, but x cannot equal 2. That is very important to remember. It's very important, right? X cannot equal 2. Well, what can I do in this function to make it more, so I can work it out, to make it more explicit, so I can evaluate, right, to a certain value. What can I do? Okay, let's factor out on the top. Let's factor out x squared, and then inside I get x minus 2. Okay, and right here I get what? In the bottom I get 3 times x minus 2, right? So notice that this x minus 2 with that x minus 2 cancels out, right? So the limit as x approaches 2, right? Now look at this. Look at this. That this is nothing but x squared over 3. Now, see, now this is a regular parabola. So what I can do now, I can just plug in 2, okay, because now 2 works for this function. So therefore I have no problem plugging in 2 in this function. So I get 2 squared over 3, which is nothing but 4/3, right? Oh, 4/3 is a real number, right? No problem. Okay, so let's prove something. What is 4/3? 4/3, I'm going to use the calculator so I can get the decimals. 4/3 is very close to that number, and also is very close to that number. Wow, that's making sense, isn't it? So that means that 4/3 is the limit, the approaching this the limit as x get close to 2. Okay? But let me raise this. Okay, so we know that L is equal to 4/3. Okay? Okay. Okay. Now we need to be careful. We're going to make a little Cartesian plane, which my drawing is not the best, but hopefully you get the idea. Okay, so I'm going to make a little parabola. Okay? Okay, so I got it 1, 2. I got it 1, 2. Okay, so at x equal 2, okay, at x equal 2, let me just move this a little bit up, okay? At x equal 2, this is 1, this is 2. At x equal 2, okay, hold on a second, let me see. It's going to be up a little bit. Okay. At x equal 2, this limiting real number 2 comma 4/3, right? But notice, and this is a very important thing that we need to know over here. We need to understand that because in the original function, a cannot equal 2, okay? I'm sorry. Yes, a cannot equal 2. Or you can say that x cannot equal 2. Notice that I need to have an empty circle. Why do I need to have an empty circle? Well, because at that point, the function was undefined. Even though I got a real number as a limit after I simplify it, but still the function is undefined. Therefore, I need to put an empty circle at x equal 2. Okay? So this is one of the examples that we need to try to understand as much we can how we are going to make sense out of this limit. And the easiest is by answering the 2 questions. The easiest way is by answering these 2 questions. If we can answer these 2 questions, this part right here, the mathematics, becomes easy, right? So that's it. See, this is x, and this is y. This is x. Okay, so that's it for this example. Okay, and let me try to do one problem a little quick. This is going to be number 13 on the book. So hopefully we can get it done quick. Okay. It's going to be number 13 in this calculus book. It's called Calculus, the Classic Edition. Okay, so we are going to do number 13. Number 13. Number 13, I got limit, I got x squared minus 4 over x minus 2, limit as x approaches 2. Okay? This is a similar problem. Okay? Okay, let's figure it out again. Can we plug into this function? Okay, can we plug into this function? Okay, if I plug in 2, then it's going to be nothing but 2 squared minus 4 over 2 minus 2, which is going to be 4 minus 4 over 2 minus 2, which is going to be 0 over 0 again. Okay? So that means that if I plug in 2, just by plugging it in, it doesn't work. Okay? Because 0 over 0 is undefined. Okay? So what I need to do, I need to factor out and see what I can do with this function. Okay? If I factor out the top, I get what? I get x plus 1, x plus 2 times x minus 2, right? And what I'm going to do, I'm going to go ahead and x minus 2 in the bottom, okay? Now I have two like factors. I cancel those out and I get x plus 2, right? Now the function is equal to that. Oh, but what is this? This is nothing but a straight line. Okay? A straight line with a slope of 1 and y-intercept of 2 at 2, right? So now I know that it's going to be the same thing. I am going to include, if you want to graph this, I'm going to do exactly the same thing as I did in the last example, but in this case, I have no problem substituting the 2 exactly at x equal to. Why? Because I have a straight line. I don't have to divide by 0 in this one, okay? So limit as x approaches 2, okay? So therefore 2 plus 2, okay? The limit is equal to 4. Okay? So the limit is equal to 4, okay? So the limit is equal to 4. Now, if your teacher tells you to graph it, then you do the same thing that we did the other one, all right? By saying that you need an empty circle at x equal 2, because at 2 the original function was undefined, okay? But this is the answer for this. The limit of this problem is 4, right? So I hope this helped, and probably I will do some more limit problems, because I think this is a very important part of calculus that we need to understand, okay? Thank you for watching, and I hope this helped anybody who was taking calculus 1 and they are doing limits, right? So thank you for watching. All right, thanks.